When you're setting up your turbulent flow calculation, you have to choose both a turbulence model and a near-wall treatment for the model that you've selected. There's no way to explain how to choose the near-wall treatment without discussing some characteristics of turbulent boundary layers. I'll keep the theory part as light as possible, and it will help to provide context and background that you'll need to understand how different near-wall treatments work and how to decide which one to choose. The boundary layer is a thin layer of fluid adjacent to a solid surface in which the velocity goes from 0 at the wall to the free stream value at some distance away from the wall. The frictional drag on a surface and most of the heat transfer take place within the boundary layer. In comparison with laminar flows, much higher gradients are observed in the boundary layer of turbulent flows, and this creates some challenges for CFD calculations. Within a turbulent boundary layer, different regions can be identified. Very, very close to the wall, the shape of the velocity profile is governed by the viscosity of the fluid, and this region is known as the viscous sublayer. Further from the wall, turbulence becomes more important than viscosity in determining the shape of the velocity profile, and this region is called the fully turbulent region. This is still fairly close to the wall, just not quite as close as the viscous sublayer. Between the two regions is a buffer region, where both viscosity and turbulence effects are important. As we'll see in a minute, the regions that are most important for CFD are the viscous sublayer and the fully turbulent region. To deal with the turbulent boundary layer in CFD, we can choose from one of two different approaches. One method is to resolve the steep profiles within the viscous sublayer by using a very fine mesh. This method is known as the viscous sublayer resolving method. It can become expensive at high Reynolds numbers due to the large number of mesh cells required. Luckily for us, it has been found that when we reformulate the velocity profile using certain non-dimensional variables, all turbulent boundary layers have the same velocity and temperature profiles. There's a second method for dealing with boundary layers that makes use of this universal behavior so that we don't have to resolve the viscous sublayer with the mesh. We can see how this works by starting with the velocity profile shown here in the slide. The y-axis is the velocity, and the x-axis is the distance from the wall. Using the friction velocity, which is defined as the square root of the wall shear stress divided by the density, dimensionless variables for velocity and wall distance can be formulated. These variables are called u plus and y plus. When these variables are used to plot the velocity with a logarithmic scale on the x-axis, the velocity profile looks like the picture here, where there's a predictable and universal shape to the velocity profile that transitions from a linear function of y plus in the viscous sublayer to a logarithmic function of y plus in the logarithmic region. The velocity profiles from two different flows are shown here. You can see that close enough to the wall, the dimensionless profiles are the same, and that for different flows, the logarithmic region extends to higher values of y plus as the Reynolds number of the system increases. These profiles are known as the universal law of the wall, or also just the law of the wall, and it forms the basis for the second method of handling turbulent boundary layers in CFD. This method is known as wall functions. The way it works is that the first grid point is located in the log layer, and empirical functions are used to impose suitable conditions close to the wall without having to resolve all the way through the viscous sublayer with the mesh. The two methods are shown here side by side for comparison. You can see that if wall functions are used, then comparatively fewer grid points are needed in the boundary layer. From this, it might be tempting to conclude that wall functions are always better, because you don't need as many grid points. But unfortunately, wall functions have certain limitations, and for that reason, it's usually more accurate to resolve the viscous sublayer with the grid, especially in problems involving flow separation or heat transfer. Because of this trade-off between accuracy and computational expense, sometimes you will use one method, and sometimes the other, but the important thing is that you will have to decide ahead of time and create your mesh based on which method you are planning to use. So to summarize, there are two approaches you can use for turbulent boundary layers: the viscous sublayer resolving approach or the wall function approach. Now that we have learned about the two different approaches that can be used for near wall modeling in turbulent flows, let's talk about how to create a suitable mesh for each of these approaches, and how to enter near wall treatment settings in Fluent. Wall functions are based on the law of the wall, which is valid for attached flow with favorable or zero pressure gradient, and on relatively simple flow geometry, such as flat plates or channel flows. They would be applicable for the flow on the left because the flow remains attached, but on the right there is flow separation on the upper surface of the ellipse, and wall functions would not be applicable. For this case, and many other cases where separation takes place due to an adverse pressure gradient, it's recommended to use the viscous sublayer resolving approach instead. This approach is also more accurate for heat transfer simulations, including natural convection, and for cases with flow impingement, and also any cases requiring accurate prediction of skin friction, which means that for the case on the left, even though wall functions might be applicable, the viscous sublayer resolving approach might be more accurate if you can afford to create a fine enough mesh. Once you decide which approach to use, you have to create a mesh suitable for that approach. The mesh resolution requirements are normally expressed in terms of Y+. To create a viscous sublayer resolving mesh, the Y+ value of the wall adjacent cell should be approximately equal to 1. However, you have to be careful in how you interpret this guideline, because Y+ equals 1 is not a magic formula. If Y+ of the first cell is approximately 1, and the growth rate of the inflation layers away from the wall is moderate, say 1.2 or lower, and there are a sufficient number of inflation layers from the wall throughout the boundary layer, then the CFD mesh will be suitable for resolving the gradients that are present in that region of the flow. For a wall function mesh, Y+ of the wall adjacent cell should be selected so that the first grid point is located in the logarithmic region of the boundary layer. A quick and dirty guideline that's often recommended is for Y+ to be between 30 and 300, but please be very careful in how you interpret this. If the Reynolds number is very high, like in an atmospheric boundary layer flow, much higher values of Y+ are acceptable, while at the other end of the spectrum, if the Reynolds number is very low, but still turbulent, wall functions might not be suitable at all, even if Y+ is in that range. So whenever you see this recommendation for Y+ and wall functions, please remember that it's not an absolute requirement. It's just an approximate guideline that works for many flows, but certainly not for all flows. What is important is for Y+ to be in the logarithmic region. When you create your mesh, you'll have to calculate the physical wall distance that corresponds to the value of Y+ that you want to use. So now that we know the mesh requirements, let's move on to input settings for near wall modeling in Fluent. If the viscous sublayer resolving approach is being used, you can use any of the k-omega models, or you can use any of the k-epsilon models, together with the enhanced wall treatment selection that you see here. When you use a k-omega model, no additional input is needed. If the wall function approach is being used, then for k-epsilon models, in most cases, you should select either scalable wall functions or enhanced wall treatment. Scalable wall functions and enhanced wall treatment are both what are known as Y+ insensitive treatments, which is important because it allows you to obtain a grid-independent solution if you refine the mesh. I prefer enhanced wall treatment myself because it will automatically switch between wall functions and viscous sublayer resolution based on Y+, and it will blend between the two if the first grid point happens to fall in the buffer region. If you are using one of the k-omega models with the wall function approach, again, no additional input is required because they automatically use a Y+ insensitive wall treatment, and they'll behave like wall functions if you have a wall function type of mesh. But it should be noted that the advantages of k-omega models may be lost when a wall function mesh is used. The input settings are important, so let's summarize. If the viscous sublayer is being resolved, you can use either the k-omega models or the k-epsilon models plus enhanced wall treatment. And if you're using the wall function approach, you can use the k-epsilon models with either scalable wall functions or enhanced wall treatment, or you can also use the k-omega models with the wall function mesh.